Hello everyone, Professor Dustin here, and this video is going to be a solution to the crates in a lift whiteboard. So in this whiteboard we have two crates sitting on top of each other, also in the floor of an elevator. And the elevator floor is exerting an upwards force on a certain amount, 1050 newtons, on the 60 kilogram crate, and we want to know a few things about magnitude and direction of the various forces involved in this problem. So if we look a little bit more carefully, we can see that first we're going to find the magnitude and direction of the acceleration of the crates in the elevator, then magnitude and direction of the contact force between the crates, and then the contact force between the crates again. So first we're going to find the contact force between 40 and 60, and then 60 and 40. So we're going to have to use two free body diagrams to answer B and C, certainly, because to get the contact force between two objects, you need to have a free body diagram for each one individually. But finding the magnitude and acceleration of the crates in the elevator, that sounds we want just like a single free body diagram that represents both of them. So I'm going to start with a single free body diagram for both to answer A. And to just be clear about that, that's my free body diagram, and I'm going to write, just to be super clear, m is m1 plus m2, just to make sure we all know that we're talking about the total mass of both the crates together. So there's the downward force due to gravity, that's going to be Fg. There's an upwards force, which is going to be the normal force, that's going to be what the elevator is doing on the crates. I didn't write them in the same size, but I'm going to figure out what direction the elevator is actually going to be accelerating in. Actually, at this stage, we don't care which crate is on the bottom. All we care is that the elevator is pushing on one of them. In fact, it's the 60 kilogram crate on the bottom. So this is just going to be a sum of all the forces in the y direction. We're not going to worry about the x direction because there's no forces in the x direction. And there's just two forces, the normal force pushing up, the gravitational force pushing down. It's the total mass of both the crates together is equal to mg, and that is going to be equal to the mass times the acceleration. So it's easy to find the acceleration just by solving this for Fn minus mg divided by the total mass. And if you put that into your calculator, you can actually write that a little simpler just by Fn over the mass minus g. The mass will cancel with the mass next to g, but it won't cancel with respect to the n, so you have to keep it as Fn over mass minus g. But anyway, that answer is, looks like 0.69 meters per second squared. So if I want to report the magnitude, that is the magnitude already, direction upwards. Okay, so to continue with part B, we need to find the magnitude and the direction of the contact force that the 40 kilogram crate exerts on the 60 kilogram crate. So we are going to need two free body diagrams. So the first one is going to be of the 40 one, that's the one on the top, and the second one will be the 60 kilogram one is the one on the bottom. So we need to think about what forces are acting on each of these crates. And actually, let me get a picture over here. So here's the big one, here's the small one, 40 and 60. Just labeling them as 40 and 60. And actually, let's just go A and B, why not? So the forces that are acting on A, well, first of all, there's a gravitational force acting on both of them, right? It's different because they have different masses. So this is going to be Fg B. And then it's bigger, so I'll just make it bigger, FGA. So then let's start with looking just at the free body diagram for B. What other forces are acting on B? Well, B is sitting on top of A, so there's a contact force in between B and A. Now the elevator is here, which is pushing upwards on A, but B doesn't feel the elevator at all. It only feels A. So I'm going to call that Fn. Actually, let me not call it Fn. Let's think about contact forces, and let me call that A on B, where the order suggests that A is acting on B, which is what's happening. The direction is just because box of B is on top of box A. So what I like to do is every time I write a force that I know has a Newton's third law pair in my diagram, I like to add that Newton's third law pair. So because A is pushing upwards on B, B is pushing downwards on A. That's the equal and opposite force. It's the same size, it's pointed downwards, it's something like that. It is now acting on B, on A from B, so that's going to be FBA. So from Newton's third law, we know that those two forces are equal and opposite, but I'm going to label them differently just to keep track of them. So finally, we have to say, well, does that accurately describe the behavior that A is actually experiencing? No, it doesn't, because we know that there's an acceleration on this object, and in fact the elevator is actually acting on A. The upwards force is actually 1050. We know how big the upwards force is on crate A. And in fact, because we know the acceleration is upwards, we know that the normal force the elevator is pushing on A is actually greater than the sum of the gravitational force and the other force. I can't really draw that because I'm running out of room, but it's anyway, that is big. That's the normal force between the elevator and block B. So now I'm going to write down Newton's second law. I haven't really thought about like exactly what thing I'm solving for, but I do know that I can do Newton's second law in the y direction. So this is going to be the sum of the forces in the y direction. Let's first do on A. So I've got an upwards force, that's the normal force from the elevator, and I have two other forces, FBA and FGA. And actually, let me not write FGA, let me actually put in the gravitational force, because we know what that is. We put the direction in already, so let's just write MGA, MAG. And that's going to be equal to MA, and of course I'm on block A, so it's got to be the mass of A times the acceleration. And I know the acceleration from the first part of this problem. Okay, let me do the same thing for block B. There are two forces on block B, FAB, minus, and again let's write MB times G. That's equal to M times A of block B, where they have the same acceleration. That's a property of objects being coupled, is that they move the same. Their velocity and accelerations are going to be the same. So now let's think about what thing we're actually trying to find. We want the magnitude and direction of the contact force that the 40 kilogram crate exerts on the 60 kilogram crate. So to me, that is B on A. So looking at our free body diagrams, FB on A is right here. So in order to solve for that, we have to make sure that we can actually solve this whole equation. And indeed, I think we can. We know what the normal force is. We know the mass of A, and we indeed found the acceleration in the previous part. So I can just solve this equation for FBA to find the answer to this. So solving that, I have to be a little bit careful because there's a negative sign here. So I moved this to the other side, left this guy and this guy, and then moved the MA times the acceleration to the other side. If I do that, I get about 420 newtons as the downwards force of FB on A, so I should say downwards for the direction. And that gives me my answer to part B. Now, to answer part C, determine the magnitude and direction of the contact force that the 60 kilogram crate exerts on the 40 kilogram crate. We want to be careful in our notation. That means we're looking for F, A on B. But of course, because of Newton's third law, we know that FA on B, it's right here, it's acting on a different object, but it's the same size as FB on A. So the answer to FA on B is, again, 420 newtons, but now it's pointed upwards. So I didn't have to do any actual work there. Actually, it would have been a little bit easier to do part C first, because this equation is slightly easier to evaluate this, because there's only two terms, but it doesn't matter. It was reasonably easy to pull this equation out first, because it's only got three terms, and we knew what they all were, so it was pretty easy to do. Okay, cool. So that's been a solution to crates on a lift. It's one of these coupled motion problems where you could do this backwards. You could even have these two equations here with A being an unknown, solve for A and plug it into this, and then find the contact forces. But it is a little bit easier to group them together first to find the acceleration, and then later split them up into two to find the individual contact forces. So that's the lesson here, is that when you need to find the contact force between two objects, you're typically having to split the objects up into two, do two free body diagrams, but that usually makes the problem fall apart pretty quickly, as long as you're careful about where the contact forces are and which object each contact force is actually acting on. Okay, great. Thanks very much for listening to this. I hope it's been helpful, and I will see you later.